You are sitting in a room that feels stable. The floor beneath you seems solid. The air seems continuous. The light appears to travel in straight lines from its source to your eyes. Your body occupies space. Time is moving forward. Causes produce effects. You assume that what exists continues to exist, whether or not you are looking at it. Nothing in this moment feels fragile. And yet, almost every one of those assumptions has already been challenged by physics. The solidity beneath you is mostly empty space. The flow of time may not be fundamental. The separation between objects might be an illusion of scale. The past may not be as fixed as you believe. The universe itself may not be made of matter at its deepest level. Even the idea that reality exists independently of observation has been called into question by carefully designed experiments. These are not fringe speculations. They emerge from quantum mechanics, cosmology, relativity, and information theory. They are supported by mathematics that predicts experimental outcomes with extraordinary precision. They are taken seriously by physicists who build satellites, particle accelerators, and gravitational wave detectors. The unsettling part is not that these theories are strange. The unsettling part is that they work. If the equations are correct, then the world you experience may be a surface phenomenon resting on structures that defy intuition. Space may be emergent, time may be relational, matter may be excitation, identity may be distributed, causality may not be absolute. You have been living inside a model that feels complete. But what if that model is only an approximation? What if reality, at its deepest level, is nothing like what your senses evolved to perceive? Tonight, you will examine 10 scientific theories that do not merely extend our understanding of the universe, but threaten to revise it at the most fundamental level. And as each one unfolds, a more difficult question will begin to surface. If reality is not what it appears to be, then what exactly are you standing on? The illusion of solidity. You trust that the objects around you are solid because your senses insist that they are. When your hand meets a table, you feel resistance. When you press against a wall, it pushes back. Solidity feels immediate and undeniable. Yet at the atomic level, the atoms that compose that table are mostly empty space, their nuclei separated by vast distances relative to their size. What you experience as contact is not matter touching matter, but electromagnetic fields repelling one another. The solid world is a structure of forces, not substance. If you could shrink yourself down to the scale of atoms, the table would not resemble a dense slab. It would look more like a sparse constellation. At the center of each atom sits a nucleus, incredibly small and incredibly dense. Around it, electrons do not orbit like planets in neat circles. They exist as probability distributions, diffuse clouds described by wave functions. Between the nucleus and these clouds lies space so vast, relative to their size, that the atom is almost entirely void. And yet, you cannot pass your hand through the table. The reason is not that the atoms interlock like rigid spheres. It is that electrons carry charge. When the electron clouds of your hand approach the electron clouds of the table, electromagnetic forces intensify. Like charges repel. The Pauli exclusion principle further prevents identical fermions from occupying the same quantum state. The result is resistance. The sensation of solidity is the macroscopic expression of microscopic rules. What you feel is force. The implication is subtle but destabilizing. The objects around you are not solid in the way they appear. They are dynamic equilibria of interacting fields. Their stability arises from balance, not from compactness. If the electromagnetic force were slightly weaker, matter as you know it would not hold together. If quantum mechanical principles were different, atoms would collapse or disperse. Solidity is not fundamental. It is conditional. This challenges an intuition you rely on constantly, that there is something inherently substantial beneath your touch. Instead, matter reduces to excitations in quantum fields. In quantum field theory, electrons are not tiny pellets embedded in space. They are localized vibrations of an electron field that permeates all of space. Protons and neutrons are themselves bound states of quarks, held together by the strong nuclear force mediated by gluons. Even the nucleus, which feels dense compared to the rest of the atom, is a dynamic system of confined energy. At deeper levels, solidity dissolves into interaction. Consider what this means for the boundary between you and the world. Your skin feels like a limit. It marks where you end and the table begins. But at the atomic level, there is no sharp dividing line. There are overlapping fields, exchanging forces. The distinction between inside and outside becomes a matter of convention at human scales. The world you navigate is therefore a stable pattern of relationships. When you sit in a chair, you are not resting on a block of substance. You are suspended by electromagnetic repulsion. When you stand on the ground, you are not truly touching it in the classical sense. There is always a minuscule gap enforced by quantum principles. Direct contact, as you imagine it, never occurs. This does not make the world unreal. It makes it stranger. Your brain evolved to interpret force as solidity because it needed a reliable model. A world of empty space, structured by invisible fields, would not be useful for survival. So perception compresses complexity into certainty. It gives you surfaces, textures, hardness, but beneath that compression lies a different ontology. If the table is mostly empty space, and if your body is mostly empty space, then the stability of your environment depends entirely on invisible constraints. The everyday world is not built from continuous substance. It is sustained by mathematical symmetries and force carriers. You are not standing on matter, you are standing on interactions. And if solidity itself is emergent, then one of your most basic assumptions about reality has already dissolved. The vacuum that is not empty. You imagine empty space as nothingness, a void devoid of structure. But quantum field theory describes a vacuum that seethes with fluctuations. Even in perfect emptiness, the virtual particles briefly appear and vanish, permitted by the uncertainty principle. Experiments measuring the Casimir effect have confirmed that this vacuum has measurable energy. The absence of matter is not the absence of activity. What you call empty may be a restless foundation. You are accustomed to thinking of space as a stage, a neutral backdrop against which matter moves and events unfold. Remove the actors, and the stage remains. Remove the props, and there is still emptiness. But modern physics does not describe space as passive. It describes it as structured by fields that cannot be switched off. In quantum field theory, every type of particle corresponds to a field that permeates all of space. Even when no particles are present, the fields remain. And because of the uncertainty principle, these fields cannot sit perfectly still, There is no configuration of absolute zero motion. Energy and time cannot both be precisely fixed. As a result, the vacuum is never truly quiet. Fluctuations occur spontaneously. Pairs of particles and antiparticles can briefly emerge from the vacuum, borrowing energy within the limits allowed by quantum uncertainty before annihilating and returning that energy. These are called virtual particles. They are not directly observable in isolation, but their effects are measurable. The vacuum influences measurable quantities, such as the Lamb shift in atomic spectra and the force between closely spaced metal plates. When two conducting plates are placed extremely close together in empty space, they experience an attractive force. This is the Casimir effect. It arises because the quantum fluctuations between the plates differ from those outside them. Certain modes of the electromagnetic field are restricted in the gap, creating a pressure imbalance. The plates are pushed together not by matter, but by differences in vacuum energy. You can measure this force. This means that emptiness exerts pressure. The implications extend beyond laboratory setups. If the vacuum possesses energy, then space itself contributes to the dynamics of the universe. In cosmology, a form of vacuum energy is one of the leading explanations for the observed accelerated expansion of the universe. What appears to be empty intergalactic space may contain an intrinsic energy density driving galaxies apart. Nothingness on the largest scale may be responsible for cosmic evolution. This challenges another assumption you rarely question, that absence is inert. When you clear a room of objects, you assume you are left with emptiness. But at the quantum level, absence is structured. It is defined by the lowest possible energy state of fields, and that state is not zero. It is a minimum, not a void. If space cannot be emptied, then there is no true vacuum in the classical sense. Even in regions between galaxies, far from stars and dust, the fields remain. They fluctuate, they store energy, they shape the behavior of particles passing through. The vacuum is not a blank page, it is an active participant. This reframes the concept of nothing. When you ask why there is something rather than nothing, you may be assuming that nothing is a coherent option, but physics suggests that the state of absolute nothingness may not be physically realizable. The laws governing fields and uncertainty prevent total stillness. Structure persists even in the lowest energy configuration. You are living in a universe where emptiness has properties. Every movement you make, every photon that reaches your eyes, travels through a medium that is not empty, but structured at a fundamental level. The background of existence is not silence, it is a quiet fluctuation. And if the vacuum itself is dynamic, then the foundation of reality is not static substance, but restless fields that never fully disappear. Entanglement and the end of separation. You assume that distance separates objects, that what happens here cannot instantly affect something far away. Yet quantum entanglement demonstrates correlations between particles that persist regardless of spatial separation. When two particles share a quantum state, measuring one influences the description of the other, even across vast distances. Bell-teased experiments have repeatedly confirmed this. The universe may not be composed of isolated pieces. It may be woven into a single, non-local structure. Your intuition tells you that space enforces independence. Two coins placed on opposite sides of the planet cannot coordinate their outcomes without some signal passing between them. Information must travel, and it cannot exceed the speed of light. This is not only common sense, it is embedded in relativity. Entanglement respects that speed limit, and yet it unsettles it. When two particles interact in certain ways, their quantum states can become linked. Instead of each particle having its own independent description, they share a single joint wave function. You can separate them by meters, by continents, even in principle by light years. The mathematics does not change. The system must be described as a whole. If you measure one particle's property, such as its spin along a chosen axis, you obtain a definite outcome. Instantly, the other particle's correlated property is fixed relative to that measurement, even if it is far away. The results are not random in isolation. They exhibit statistical correlations stronger than any classical theory, allowing local hidden variables can produce. This is not philosophical speculation, it has been tested. Experiments inspired by Bell's theorem have repeatedly demonstrated violations of Bell inequalities. These inequalities define the limits of correlations achievable by any local realist theory, one in which properties are predetermined and no influence travels faster than light. The experimental data contradict those limits. Nature does not conform to local realism. You cannot use entanglement to send messages faster than light. The outcomes are individually random, but once results are compared, the correlations are undeniable. The structure of the data cannot be explained by pre-existing hidden instructions carried by each particle from the moment of separation. Something deeper is occurring. The unsettling possibility is that spatial separation does not imply ontological separation. At the fundamental level, the universe may not consist of independently existing parts stitched together by forces. Instead, what you call separate objects may be emergent from an underlying, indivisible quantum state. Distance, in this view, is not the primary divider. You experience yourself as distinct from distant stars. You assume that events occurring billions of light years away are entirely independent of your immediate surroundings, and at the level of classical physics, this independence holds. But at the quantum level, the fabric appears continuous. Entanglement suggests that the most complete description of reality is not local. The properties of a part cannot always be specified without reference to the whole. The universe may be less like a collection of marbles in space and more like a single equation whose terms cannot be factored cleanly apart. This does not mean that everything is entangled with everything else in any simple, usable sense. Decoherence rapidly suppresses observable quantum correlations at macroscopic scales. Your everyday world appears classical because interactions with the environment effectively isolate systems. But the classical appearance is layered on top of quantum non-locality. The deeper description remains holistic. If the universe at its foundation resists decomposition into fully independent pieces, then the concept of isolation is approximate. The boundaries you perceive between objects, between systems, even between yourself and the rest of the cosmos, may not be fundamental divisions. They may be emergent conveniences. You navigate a world of separate things because that model works at your scale. Yet beneath that scale, reality does not honor strict separations. It honors correlations that transcend distance. And if separation itself is not absolute, then the structure of reality is not a collection of isolated entities. It is a web. The relativity of time. You feel time passing at a constant rate. Seconds seem universal, but relativity has shown that time is elastic. Clocks on fast-moving satellites tick differently than clocks on Earth. Gravity slows time near massive objects. Time does not flow identically for all observers. It bends with motion and mass. What you experience as a shared present is not shared at all. Your intuition tells you that time is a steady backdrop. It advances uniformly, indifferent to what moves within it. A second here is a second anywhere. You assume that if two clocks are synchronized and separated, they remain in agreement unless one is broken. Relativity dismantles this assumption. According to special relativity, the rate at which time passes depends on relative velocity. If you travel at speeds approaching that of light, your clock will tick more slowly compared to a stationary observer. This is not an illusion or a mechanical error. It is a consequence of the structure of space-time itself. Time dilates to preserve the invariant speed of light. This effect has been measured repeatedly. Atomic clocks flown on high-speed aircraft and placed aboard satellites accumulate measurable differences compared to identical clocks on the ground. The global positioning system must account for both velocity-based time dilation and gravitational time dilation to maintain accuracy. Without relativistic corrections, GPS would drift by kilometers each day. You rely on relativity every time you navigate. General relativity extends the effect further. Gravity is not a force pulling objects through space. It is the curvature of space-time caused by mass and energy. Where space-time curves, clocks tick differently. The stronger the gravitational field, the slower time flows relative to regions with weaker gravity. Near a massive object, such as a neutron star or a black hole, time slows dramatically. To a distant observer, a clock approaching the event horizon of a black hole appears to slow nearly to a stop. From the perspective of the falling clock, however, time feels normal. Both descriptions are valid within their frames of reference. There is no universal tempo. This leads to a destabilizing realization. There is no single, objective present moment shared by the entire universe. Two observers, moving relative to each other, will disagree about which events are happening simultaneously. What you consider happening now may, for another observer in motion, belong to the past or the future. Simultaneity is relative. You experience a flowing present that seems to slice cleanly through reality, separating what has happened from what has not. But relativity suggests that this slice is perspective dependent. The division between past, present, and future is not absolute. It depends on how you are moving and where you are located within gravitational fields. Time is not a river carrying everything forward in unison. It is a dimension intertwined with space, forming a four-dimensional space-time. Different observers trace different paths through this structure, and along those paths, the duration between events varies. Your biological rhythms give you the impression of uniform passage, but physics reveals flexibility beneath that impression. If time can stretch and compress, depending on motion and gravity, then your personal experience of duration is local. It does not define the tempo of the cosmos. There is no master clock governing all processes. You inhabit a relativistic web where each world line carries its own measure of time. This does not make your experience false. It makes it partial. The seconds you count are real along your path, but they are not privileged. Somewhere in the universe, time is moving more slowly relative to you. Somewhere else, more quickly. The shared present you assume binds everyone together does not exist in the way you imagine. Time does not flow identically for all observers. It bends, and in bending, it fractures the idea of a single universal now, the block universe. You experience time as unfolding. The future does not yet exist. The past is gone. But in the block universe interpretation of relativity, all moments coexist within a four-dimensional space-time structure. Past, present, and future are equally real. The flow of time may be a feature of consciousness moving along a static timeline. If so, the sense of becoming is not fundamental. Your entire life is organized around the idea of temporal passage. You anticipate what has not yet happened. You remember what no longer exists. You feel suspended in a thin edge, called the present, advancing moment by moment into an open future. Relativity does not describe such an edge. In the mathematical structure of space-time, events are represented as coordinates in a four-dimensional continuum. Just as every location in space exists within the spatial manifold, every moment exists within space-time. The equations do not privilege one moment as objectively present. They describe a completed geometric structure. In this view, the universe is not something that unfolds. It is something that is. Imagine a map laid out in full. Every road, every city, every boundary is present on the page simultaneously. A traveler moving along a route experiences progression, but the map itself does not change. The block universe suggests that reality may be similar. Your experience of moving from past to future may correspond to tracing a path through an already existing structure. Nothing is added to the block as time passes. The sense that the future is open and the past fixed may arise from asymmetries in information and entropy, not from the ontological status of events. You remember yesterday because physical records exist in your brain and environment. You do not remember tomorrow because no such records are accessible to you. But from a space-time perspective, tomorrow's events occupy coordinates just as real as those of yesterday. This does not mean you can access them. It means that existence may not depend on your awareness of it. The unsettling consequence is that change might be a matter of perspective. The birth of a star, the fall of a civilization, your next thought, and your final breath could all be embedded within the space-time manifold. From within your world line, you experience them sequentially. From outside that perspective, the sequence is a static pattern. Becoming may be psychological rather than fundamental. This interpretation is not imposed by speculation alone. It arises naturally from the relativity of simultaneity. If different observers disagree about which events are happening now, then there can be no single global present slicing through the universe. Without a universal present, it becomes difficult to defend the idea that only one moment truly exists. Instead, all moments may coexist, arranged along temporal dimensions, just as locations coexist along spatial ones. This challenges the core of your identity. You think of yourself as a dynamic entity moving through time, but in the block universe, you are a four-dimensional object, extended across space-time. The child you once were and the person you will become are not erased or unreal. They occupy different temporal regions of the same structure. You do not pass from one to the other. You are all of them, distributed along your world line. From within the structure, you experience motion and growth. From a higher dimensional description, you are a fixed geometric form. This does not eliminate free will in any simple sense, but it reframes it. Choices may be part of the block, not external inputs shaping it from outside time. The feeling of openness may correspond to your limited perspective within the structure, not to indeterminacy in existence itself. If the block universe is correct, then the passage of time is not a fundamental feature of reality. It is a feature of how you inhabit it. And the future you imagine as unwritten may already be written into the geometry of space-time, waiting not to be created, but to be encountered. The simulation hypothesis. You assume the universe is made of physical substance. Yet some physicists and philosophers have considered the possibility that reality is fundamentally informational. If the laws of physics are computable, if space is quantized, if information has limits, then the universe may resemble a simulation. This does not prove it is one, but it raises a measurable question. Are there detectable constraints consistent with computational architecture? Your everyday experience suggests that matter is primary. Objects exist, and information describes them. A book contains words because ink rests on paper. A computer stores data because physical components occupy states. Substance comes first, representation follows. But modern physics has gradually inverted this intuition. The black hole thermodynamics implies that information is not optional. When matter falls into a black hole, its physical details appear lost, yet the laws of quantum mechanics forbid the destruction of information. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This suggests that information may be more fundamental than the three-dimensional space it appears to occupy. At the quantum level, particles are described by mathematical states encoding probabilities. Physical properties are extracted from these informational structures through measurement. Increasingly, the language of fundamental physics is the language of bits, entropy, and computation. If reality at its core is informational, then the distinction between physical and simulated becomes less clear. A simulation is, in essence, the rule-governed evolution of information. If the laws of physics are algorithmic, if the universe evolves according to mathematically precise updates, then its behavior resembles computation. Cellular automata and digital physics models explore whether space-time itself could be discrete, updating in finite steps rather than flowing continuously. You already know that space and time may not be infinitely divisible. At the Planck scale, current theories suggest limits beyond which classical notions of distance and duration break down. There may be a smallest meaningful unit of length and time. If so, reality is not smooth, but granular. Granularity resembles pixelation. If the universe has a maximum information density, a maximum processing speed, and finite resolution, these features parallel computational systems. The speed of light can be interpreted as a maximum rate of information transfer. The Bekenstein bound places a limit on the amount of information that can be stored within a finite region of space containing finite energy. These are not arguments that you are inside a computer in any literal sense. They are structural analogies grounded in physical law. The simulation hypothesis takes a further step. It asks whether a sufficiently advanced civilization could simulate entire universes with conscious observers. If such simulations are possible and numerous, then statistically it becomes plausible that any given observer exists within a simulation rather than base reality. This is a probabilistic argument, not an empirical one. The deeper scientific question is whether there are detectable signatures of underlying computational architecture. Could there be anisotropies in space-time, suggesting a grid? Could high-energy experiments reveal a cutoff consistent with lattice structure? Could the laws of physics exhibit compression artifacts or optimization strategies? So far, no conclusive evidence points in this direction. Yet the mere coherence of the question is destabilizing. If reality is informational at its foundation, then physical substance may be emergent from patterns of data. What you call matter would be a stable configuration within a deeper informational substrate. In that case, your body is not made of solid substance. It is a process encoded in rules. This does not trivialize existence. A simulated storm is still a storm within its system. Simulated pain, if instantiated in a conscious process, would still be pain. The distinction between real and simulated becomes ambiguous when both are defined by consistent internal structure. The unsettling possibility is not that the universe is fake, it is that physicality itself may be derivative. If the ultimate layer of reality is informational, then what you perceive as substance is the output of a deeper computation. The question is no longer whether the universe is made of matter, it is what runs the code. The holographic principle. You believe that three-dimensional space contains information within its volume, but black hole thermodynamics suggests that information is proportional not to volume, but to surface area. The holographic principle proposes that the physics within a region of space can be described by information encoded on its boundary. The depth you perceive may be emergent from a lower dimensional structure. Your intuition tells you that if you double the size of a box, you double the space inside it. More room should mean more capacity to store things. Volume feels like the natural measure of content. A larger region of space should be able to hold proportionally more information. Black holes disrupt this intuition. In the 1970s, calculations by physicists studying black hole thermodynamics revealed something unexpected. The entropy of a black hole, a measure of its information, content, is proportional not to the volume enclosed by its event horizon, but to the area of that horizon. This relationship, known as the Bekenstein-Hawking entropy formula, suggests that the maximum amount of information contained within a region of space scales with its surface area. This is not a minor correction, it is a radical constraint. If you attempt to compress too much information into a given volume, it will collapse into a black hole, and the information capacity of that black hole depends on its surface area. This implies a universal bound. The information content of any region cannot exceed a limit proportional to its boundary. Volume may not be fundamental. The holographic principle generalizes this idea. It proposes that the complete description of all phenomena occurring within a volume of space can be encoded on its boundary with one fewer spatial dimension. In certain theoretical frameworks, such as the ADs/C or VFT correspondence in string theory, This relationship is made mathematically precise. A gravitational theory in a higher dimensional space can be equivalent to a quantum field theory without gravity on its lower dimensional boundary. Two different descriptions, one bulk and one boundary, yield the same physics. If this principle extends to our universe, then the three-dimensional world you inhabit could be a projection of information encoded on a distant two-dimensional surface. The depth you perceive would not be fundamental. It would emerge from more basic relations defined on that boundary. You experience space as expansive and volumetric. You move forward and backward, left and right, up and down. But if the holographic principle is correct at a deep level, then the true degrees of freedom describing your world might reside on a lower dimensional structure. This does not mean you are flat. It means the dimensionality itself may be emergent. Consider a hologram. A two-dimensional surface encodes a pattern of interference that, when illuminated, produces the appearance of three-dimensional depth. The depth is not located in the surface in any obvious way, yet it arises from it. The holographic principle suggests that space-time itself may operate similarly. The implications extend to gravity. Some physicists have proposed that gravity may not be a fundamental force, but an emergent phenomenon arising from the statistical behavior of microscopic degrees of freedom encoded on boundaries. In this view, space-time curvature could result from entropic principles rather than being a primary feature. If space is emergent, then geometry is not the base layer of reality. The distances you measure, the volumes you enclose, the directions you move through may arise from deeper informational relationships. The familiar three-dimensional arena would be a macroscopic manifestation of underlying boundary data. This reframes your position in the cosmos. You assume you are located within a vast three-dimensional expanse, but if that expanse is a projection, then your existence is tied to a structure you cannot directly perceive. You navigate depth, but depth may not be fundamental. If the maximum information in a region depends on surface area, not volume, then the universe is more constrained than it appears. Its apparent richness is encoded economically. What feels spacious may be tightly bounded by unseen informational limits. The space around you may not be what it seems. It may be the shadow of something thinner. The many words. Interpretation. When a quantum event has multiple possible outcomes, you assume one occurs and the others do not. The many worlds interpretation suggests otherwise. Every quantum possibility may be realized in branching universes. The wave function never collapses. Instead, reality continually splits. If this is correct, there may be countless versions of you diverging with each quantum interaction. Your intuition insists on singular outcomes. The coin is either heads or tails. A particle is either detected here or there. Even in quantum mechanics, where probabilities dominate, you expect uncertainty to resolve into a single fact when measured. Standard formulations of quantum theory describe this resolution as wave function collapse. Before measurement, a system exists in a superposition of states. Upon measurement, the one outcome becomes real and the others vanish. The many worlds interpretation rejects collapse. Proposed by Hugh Everett in 1957, it takes the mathematical formalism of quantum mechanics at face value. The wave function, which evolves deterministically according to the Schrödinger equation, never collapses. Instead, when a measurement occurs, the combined system of observer and observed becomes entangled. The universal wave function branches into non-interacting components, each corresponding to a different outcome. All outcomes persist. If a particle has a 50% probability of being measured, spin up, and 50% spin down, then after measurement there exist two branches of the universe. In one, you observe spin up, in the other, you observe spin down. Each branch contains a version of you who perceives a definite result. Yet from within any given branch, it appears as though collapse has occurred. You see one outcome and not the other, but according to many worlds, the other outcome is equally real, unfolding in a parallel branch that no longer interferes with yours due to decoherence. Decoherence plays a crucial role. Interactions with the environment cause different branches of the wave function to rapidly lose coherence with one another. Interference effects become effectively impossible at macroscopic scales. The branches evolve independently, giving the appearance of classical reality. The mathematics remains continuous and unitary. This interpretation has a stark simplicity. It removes the need for an ill-defined collapse postulate. The same equations govern microscopic particles and measuring devices. There is no special rule triggered by observation. Measurement is just entanglement on a larger scale, but the cost is ontological extravagance. If the wave function of the universe encompasses all possibilities, then every quantum event with multiple outcomes produces branching structure. The number of branches grows unimaginably large. At each moment, reality differentiates into a vast multiplicity of non-communicating histories. In some branches, you made different decisions. In others, events unfolded in subtly altered ways. Most branches would be nearly identical to your current one, diverging only in microscopic details. Others would eventually diverge dramatically. You would not be aware of these counterparts. Each version of you would feel singular, continuous, and unique. None would have access to the others. Yet from the perspective of the full wave function, they would all coexist as components of a larger structure. This reframes probability. In many worlds, probabilities do not describe which outcome will occur. They describe the relative measure of branches in which each outcome is realized. Uncertainty becomes self-locating uncertainty. Before measurement, you are uncertain which future branch you will inhabit, even though all branches will exist. The unsettling implication is not merely that parallel universes might exist. It is that quantum mechanics may already require them. If the formalism is universally valid and no collapse occurs, then the multiplicity is not speculative fiction. It is the literal unfolding of the wave function. You experience a single thread of events, believing alternatives were eliminated. But under many worlds, alternatives are not destroyed. They are realized elsewhere in the branching structure. Reality does not choose, it proliferates. The heat, death of meaning. You assume that structure can persist indefinitely, but thermodynamics predicts increasing entropy. Stars burn out, energy gradients flatten. In the far future, the universe may reach heat death, a state of maximum entropy where no useful work can be extracted. Complexity depends on imbalance. If imbalance disappears, so may structure itself. Your world is defined by differences. There is warmth and cold, light and dark, pressure and vacuum. Your body functions because chemical gradients exist across membranes. Weather forms because temperature differences drive motion in the atmosphere. Stars shine because nuclear fusion releases energy from concentrated mass. Every organized process you depend on arises from imbalance. Thermodynamics describes how those imbalances evolve. The second law states that in an isolated system, entropy tends to increase. Entropy is often described as disorder, but more precisely, it measures the number of microscopic configurations consistent with a macroscopic state. Systems evolve towards states that can be realized in more ways. Energy spreads out. Differences smooth over time. Locally, entropy can decrease. Life itself is a local reduction in entropy, but this is achieved by exporting entropy elsewhere. Your body maintains order by consuming energy and releasing heat. On a cosmic scale, however, the total entropy increases. The early universe appears to have begun in a state of extraordinarily low entropy relative to its energy content. That low entropy condition allows stars to form, galaxies to coalesce, and complex chemistry to arise. It created gradients. It permitted structure, but those gradients are not permanent. Stars exhaust their nuclear fuel. They expand, collapse, or fade into remnants. Black holes evaporate over immense timescales through Hawking radiation. Matter decays. Eventually, if current cosmological models are correct, the universe will approach a state in which energy is evenly distributed, diluted by expansion. In such a state, there are no large temperature differences, no concentrated sources of free energy, no engines to drive change. This is heat death. It does not mean a sudden catastrophic event. It means gradual exhaustion, a slow fading of contrast. Over trillions upon trillions of years, structures disintegrate. The galaxies drift apart beyond each other's observable horizons. The night sky empties. Complexity requires free energy. Free energy requires gradients. Without gradients, no work can be done. No processes can sustain themselves. Your existence depends on a temporary disequilibrium. You are alive because the universe is not yet at equilibrium. The sun still burns. The earth still radiates heat into colder space. Chemical bonds still hold potential energy. But thermodynamics suggests that this is a transient phase. Eventually, if expansion continues and no new physics intervenes, the cosmos becomes thin, cold, and uniform. Photons stretch to extreme wavelengths. Black holes evaporate. What remains is a sparse distribution of low-energy particles and radiation approaching thermodynamic balance. In such a universe, nothing meaningful in the biological or structural sense persists. No memory can be stored without energy differences. No computation can occur. No life can metabolize. The unsettling aspect is not merely cosmic mortality. It is that meaning, as you understand it, depends on gradients. Your thoughts are electrochemical processes sustained by energy flow. Your memories are physical arrangements maintained against entropy. Even language relies on contrast between symbols. If the universe trends toward maximal entropy, then the long-term future contains no structure capable of supporting observers. The conditions that allow you to ask questions are temporary. Heat death reframes existence as a fleeting configuration in a thermodynamic trajectory. The complexity you inhabit is not stable. It is a transient eddy in a larger process of equilibration. You live in a window carved out by low entropy. And when that window closes, not through violence, but through uniformity, the capacity for structure itself may vanish. The universe does not promise persistence. It promises equilibrium. Emergent space. You think of space as the stage on which events occur, but some approaches to quantum gravity suggest space is not fundamental. It may emerge from networks of entanglement or informational relationships. If space is derivative, then distance itself is not primary. Geometry may be the shadow of deeper connections. Your intuition places space at the foundation of everything. Objects occupy positions. Events occur at locations. Distances separate bodies. Geometry feels like the container within which reality unfolds. Remove matter, then space remains. Yet when physicists attempt to reconcile general relativity with quantum mechanics, this foundation begins to fracture. General relativity describes gravity as the curvature of spacetime. Quantum mechanics describes matter and energy in terms of probabilistic states and fields. When pushed to extreme regimes, such as inside black holes or at the Big Bang, the smooth geometry of spacetime breaks down under quantum fluctuations. The equations no longer behave consistently. Something deeper seems required. Several approaches to quantum gravity suggest that space-time itself may not be fundamental. Instead, it could emerge from more basic, non-spatial entities. In certain theoretical frameworks, patterns of quantum entanglement appear to give rise to geometric structure. And research inspired by holography and quantum information theory indicates that the connectivity of space-time may correspond to the entanglement structure of underlying quantum states. In simplified models, altering entanglement changes the effective geometry. Reduce entanglement, and regions of space can become disconnected. This suggests that distance may reflect the strength of informational relationships. Two regions of space that appear far apart could be closely linked at a deeper level if their quantum states are highly entangled. Conversely, regions that appear adjacent might be weakly connected in the underlying structure. Geometry would then be emergent, not primitive. Loop quantum gravity takes a different but related approach. It proposes that space-time is composed of discrete elements arranged in networks known as spin networks. These networks do not presuppose a continuous background space. Instead, space emerges from combinatorial relations between fundamental units. Area and volume become quantized properties derived from these relations. In both approaches, space is not a continuous arena. It is a large-scale approximation. At sufficiently small scales, the smoothness you experience dissolves into something more abstract. Just as temperature emerges from the collective motion of molecules, spatial extension may emerge from deeper interactions. You do not perceive individual molecules when you feel warmth. You perceive an average effect. Likewise, you may not perceive the fundamental structure from which space arises. You perceive geometry because it is a stable macroscopic pattern. If space is emergent, then asking what exists at a point in space may be the wrong question. Points themselves may not be fundamental. Instead, reality could consist of relational data without predefined coordinates. Position would arise from patterns within that data. This challenges your sense of separation. You think in terms of here and there, near and far. But if distance is derivative, then separation is not absolute. The apparent expanse between galaxies may be a manifestation of underlying relational structure rather than a literal gulf. Even the expansion of the universe could be reinterpreted. Instead of space stretching like a fabric, the relational network from which space emerges might be evolving. What you interpret as increasing distance could reflect changing connectivity at a fundamental level. You move through space, believing it to be the most obvious feature of reality. Yet some of the most serious attempts to unify physics imply that space is a secondary construct. The stage may not be fundamental. It may be the projection of deeper connections you cannot directly observe. If geometry is emergent, then your position in space is not a primary fact. It is a derived property of a more abstract structure, and what you call distance may be nothing more than a measure of how information is arranged. Quantum indeterminacy. You assume that events have definite outcomes, even if unknown to you. Yet quantum mechanics describes probabilities that are not simply due to ignorance. Before measurement, certain properties do not have definite values. Indeterminacy appears intrinsic. Reality at small scales may not be fully determined until interaction occurs. Your intuition is shaped by classical physics. A coin lands heads or tails because of precise initial conditions. If you knew every force and every variable, you could predict the result. Uncertainty reflects limited knowledge, not incomplete reality. Quantum mechanics does not allow discomfort. In the quantum formalism, the state of a system is described by a wave function. This wave function encodes probabilities for different outcomes. Prior to measurement, the system can exist in a superposition of states. It is not that the particle secretly has one definite value that you have yet to uncover. Instead, the theory assigns no definite value at all until interaction forces a result. Consider the double-slit experiment. When particles such as electrons are fired toward a barrier with two openings, they produce an interference pattern characteristic of waves even when sent one at a time. Each electron behaves as though it traverses both slits simultaneously, interfering with itself. Only when a measurement is made to determine which slit it passes through does the interference pattern disappear, replaced by particle-like behavior. The act of measurement alters the outcome. This is not merely disturbance caused by clumsy instruments. It reflects the structure of the theory itself. The wave function evolves smoothly and deterministically until a measurement-like interaction yields a specific outcome, with probabilities determined by the Born rule. Various interpretations attempt to clarify what this means. Some suggest hidden variables, others propose branching universes, but the experimentally verified predictions remain the same. Certain pairs of properties, such as position and momentum, do not simultaneously possess definite values prior to measurement. The uncertainty principle is not about technical limitations, it is about the structure of reality. If indeterminacy is intrinsic, then the future is not fixed in the classical sense. At microscopic scales, events may not be determined by prior states alone. Radioactive decay, for example, occurs with a precise statistical half-life, but the exact moment a specific atom decays appears fundamentally random within the standard framework. This randomness is not chaos from ignorance. It is built into the equations. You might imagine that deeper variables could restore determinism. Yet the Bell test experiments have placed severe constraints on local, hidden variable theories. Any hidden structure must violate locality or realism in ways that challenge classical intuition. The consequence is unsettling. The world at its foundation may not consist of definite properties waiting to be revealed. It may consist of potentialities that crystallize into facts only through interaction. Measurement, then, is not passive observation. It is a physical process that establishes outcomes. This blurs the boundary between observer and system. You think of yourself as discovering pre-existing facts. Quantum mechanics suggests that in some cases, the fact did not exist in a definite form prior to interaction. Reality may not be fully specified until it is engaged. On macroscopic scales, decoherence suppresses quantum superpositions, producing the stable, definite world you experience. Tables do not appear in superpositions of locations. Cats are not observed in mixed states of life and death, but this classical stability emerges from underlying indeterminacy. Beneath the apparent solidity of events lies a probabilistic substrate. You inhabit a world that feels definite and determined, yet its smallest constituents obey rules in which possibility precedes fact. If indeterminacy is fundamental, then the unfolding of events is not the execution of a predetermined script. It is the continual resolution of probabilities into experience. The fine-tuning problem. The constants of physics appear delicately balanced. Small changes in fundamental parameters could prevent stars, chemistry, or life. This fine-tuning raises possibilities, coincidence, necessity, multiverse selection, or unknown principles. The laws that allow your existence may not be inevitable. You take for granted that the universe permits structure. Atoms form stable bonds. Stars ignite and shine for billions of years. Carbon exists. Water has unusual properties that enable complex chemistry. None of this feels improbable from inside it. But when physicists examine the numerical values of fundamental constants, a different picture emerges. The strength of gravity, the electromagnetic coupling constant, the masses of elementary particles, the cosmological constant governing cosmic expansion, all appear to lie within narrow ranges that allow complexity. If gravity were significantly stronger relative to electromagnetism, stars would burn too quickly and too violently for stable planetary systems. If it were much weaker, matter might never clump into stars at all. If the strong nuclear force were slightly weaker, atomic nuclei would not hold together. Slightly stronger, and stellar processes would convert hydrogen to heavier elements too efficiently, leaving little fuel for long-lived stars. The mass difference between protons and neutrons is tuned in a way that permits stable hydrogen. Alter it, and chemistry changes radically. Even the cosmological constant presents a puzzle. Observations indicate that it is small but positive, then driving the accelerated expansion of the universe. Theoretical estimates from quantum field theory predict a value many orders of magnitude larger. If it were even modestly larger than observed, cosmic expansion would have prevented galaxies from forming. Matter would have dispersed before gravity could gather it. The window for structure appears narrow. This does not automatically imply design or intention. It does, however, raise a question. Why do the constants take the values they do? One possibility is necessity. Perhaps deeper physical laws fix these constants uniquely. What appears contingent may be the only mathematically consistent configuration. A future unified theory might reveal that the parameters could not have been otherwise. Another possibility is coincidence. Perhaps we simply observe one particular set of values among many logically possible ones, and it happens to permit complexity. This explanation is logically consistent, but offers no deeper account. A third possibility invokes a multiverse. Some models of cosmic inflation and string theory suggest that different regions of a vast or eternal cosmos could realize different physical constants. In such a landscape, most regions would be sterile. Observers would necessarily arise only in regions where the constants permit structure. Your existence would then be a selection effect, not evidence of inevitability. You observe this universe because it allows observers. This reasoning is known as the anthropic principle. It does not predict specific values from first principles. It constrains what can be observed, given that observers exist. Critics argue that it risks explaining too much too easily. Supporters argue that if a multiverse is independently motivated by theory, anthropic reasoning may be unavoidable. The unsettling aspect is that the laws governing your existence may not be uniquely determined. They may be environmental features of a larger ensemble. The physics you treat as universal could be local. If the constants were slightly different, you would not be here to notice. This places your existence within a narrow corridor of possibility. The structure of matter, the longevity of stars, the chemistry of life, all depend on numerical relationships that do not appear dictated by logic alone. You inhabit a universe balanced on parameters that might have been otherwise. Whether this balance reflects necessity, chance, or selection across a multiverse remains unresolved. But the fine-tuning problem forces a confrontation with contingency. The laws that allow you to exist may not be inevitable. They may be one outcome among many unrealized alternatives in a space of possibilities far larger than the world you see. Dark matter. Galaxies rotate in ways that visible matter cannot explain. Gravitational lensing reveals more mass than we can see. Dark matter appears to dominate the mass of the universe, yet it does not emit light. Most of the matter shaping cosmic structure is invisible and unknown. You grow up trusting what you can see: stars, gas clouds, glowing nebulae. These seem to account for the substance of the cosmos. But when astronomers measure how fast galaxies spin, something unsettling emerges. The outer stars orbit too quickly. According to the gravity generated by visible matter alone, they should drift away into intergalactic space. They do not. They remain bound, moving as if embedded in a vast, unseen halo. The discrepancy first became impossible to ignore in the 20th century. Observations by astronomers like Vera Rubin revealed the rotation curves, the speeds of stars at different distances from galactic centers, flatten rather than decline. The equations of gravity, tested and trusted from falling apples to planetary orbits, predict one outcome. The universe delivers another. Either gravity behaves differently on cosmic scales, or there is more matter than meets the eye. Gravitational lensing strengthens the mystery. Massive objects bend light. When you observe distant galaxies, whose light is warped and stretched by intervening clusters, then you can calculate the mass required to produce such distortions. Again and again, the visible matter falls short. There is extra mass present, silent yet gravitationally decisive. The cosmos behaves as though submerged in a transparent ocean of substance that neither shines nor absorbs. You might imagine dark matter as shadowy particles drifting between stars. Yet it is not simply the absence of light. It is matter that does not interact with electromagnetic radiation in any significant way. It neither emits, reflects, nor blocks photons. Its presence is inferred solely through gravity. This makes it elusive in laboratory searches, where detection methods often rely on electromagnetic signals. On larger scales, dark matter becomes even more central. Computer simulations of cosmic evolution reveal that galaxies form within vast scaffolds of dark matter. Without this hidden framework, matter in the early universe would not have clumped efficiently enough to create the structures you now observe. The cosmic web, filaments stretching across hundreds of millions of light years, appears to trace the distribution of something fundamentally invisible. You are left confronting an inversion of intuition. The atoms composing your body, the planets, the stars, all the luminous matter you instinctively identify as the universe, may account for only a small fraction of its total mass. Most of the gravitational architecture shaping reality lies beyond direct perception. The dominant form of matter is something you have never seen. Theories attempt to fill the gap. Some propose undiscovered particles, weakly interacting massive particles, axions, or other exotic entities emerging from extensions of known physics. Massive underground detectors wait patiently for rare collisions between such particles and ordinary matter. Particle accelerators search for hints in high-energy collisions. So far, confirmation remains elusive. Others suggest that gravity itself may require revision. Perhaps on vast scales, the laws you inherited from classical physics and refined through relativity subtly shift. Modified gravity theories attempt to reproduce galactic behavior without invoking unseen matter. Yet these alternatives struggle to explain all observations simultaneously, especially the precise patterns seen in cosmic background radiation and large-scale structure. Dark matter is not merely a missing ingredient. It is a reminder that perception is provincial. Your senses evolved for survival on a narrow planetary surface, not for comprehending cosmic composition. Even your instruments extend perception only indirectly, translating gravitational effects into data you can interpret. What you call reality is already an interpretation layered atop inference, and so you exist within a universe whose dominant matter is unknown in identity, unseen in form, and yet indispensable in effect. The galaxies spin because of it. Light bends because of it. Structures assemble because of it. The visible cosmos, bright, intricate, familiar, maybe only a thin, luminous skin, stretched across a far deeper, darker foundation. Dark energy. The expansion of the universe is accelerating. Something is driving galaxies apart at increasing speed. This phenomenon, called dark energy, comprises most of the universe's energy content. Its nature remains unclear. The largest scale behavior of reality is governed by something we do not understand. You might assume that gravity, being attractive, should steadily slow cosmic expansion. After the initial impulse of the Big Bang, galaxies should decelerate as their mutual attraction pulls against their outward motion. For decades, cosmologists framed their measurements around this expectation. The question was not whether expansion would slow, but by how much. Then came the surprise. In the late 1990s, two independent teams studying distant Type 1, a supernovae, found that these stellar explosions appeared dimmer than expected. Dimmer meant farther. Farther meant that the universe had expanded more than models predicted. The conclusion was disorienting. Expansion was not slowing down. It was speeding up. The discovery reshaped cosmology. Observations from the Hubble Space Telescope and later the Planck mission refined measurements of cosmic background radiation, confirming a universe whose energy budget is dominated not by matter, visible or dark, but by something else entirely. Roughly 5% of the cosmos consists of ordinary matter. About 27% is dark matter. The remaining majority is attributed to dark energy. You are confronted with a paradox. On galactic scales, gravity binds stars into galaxies and galaxies into clusters. But on the largest scales, some opposing influence overwhelms gravity's pull, stretching space itself. Dark energy does not behave like matter. It does not clump, it does not form halos or filaments. It appears uniform, diffused throughout space-time, exerting its influence everywhere at once. One possibility is that dark energy is a property of space itself, the so-called cosmological constant, first introduced by Albert Einstein. In Einstein's equations of general relativity, empty space can possess intrinsic energy. As the universe expands, more space exists. If that space carries energy, the total amount grows. Instead of diluting, this energy remains constant per unit volume, leading to accelerated expansion. Yet this explanation opens another puzzle. Quantum field theory predicts that vacuum energy should exist, arising from fluctuations at microscopic scales. But naive calculations overshoot the observed value by an astonishing margin, many orders of magnitude larger than what cosmology permits. The mismatch between theoretical expectation and measured acceleration is one of the deepest unsolved problems in physics. Alternative models attempt to describe dark energy as a dynamic field, evolving over time. Perhaps its strength changes slowly, altering the fate of the cosmos. If it increases, expansion could become so extreme that galaxies, stars, planets, and even atoms are ultimately torn apart in a hypothetical Big Rip. If it weakens, cosmic acceleration might eventually stabilize. Current data, however, remain consistent with a constant value, offering no decisive clues. You are left contemplating scale. On human scales, gravity seems dominant. On stellar scales, it sculpts systems and ignites fusion. But on cosmological scales, an entirely different influence governs destiny. The ultimate fate of every galaxy depends less on the matter within it and more on this pervasive, invisible driver embedded in space-time itself. Dark energy also reframes your understanding of emptiness. What you call nothing, the vast voids between galaxy clusters, is not inert. It may be the very source of cosmic acceleration. Emptiness becomes active, expansive, generative. The vacuum is not void but dynamic. The unsettling implication is that most of reality's energy resides in a form you cannot detect directly, cannot isolate in laboratories, and cannot yet explain. The equations describe its effects with precision. The observations confirm its dominance, but its identity remains obscure. You inhabit a universe whose long-term trajectory is dictated by an unknown component woven into the fabric of space. Galaxies drift farther apart. Future observers, if they exist, may see a darker sky as distant structures slip beyond observable horizons. Acceleration ensures increasing isolation. The cosmos expands not merely because it began expanding, but because something continues to push. The greatest scale motion of existence is driven by a presence you have named, measured, and mathematically described, yet fundamentally do not understand. The measurement. Problem. Quantum theory predicts probabilities with extraordinary accuracy, yet it does not clearly explain how definite outcomes arise from superpositions. When does possibility become fact? What counts as a measurement? The transition from wave function to experience remains unresolved. You are accustomed to outcomes. A coin lands heads or tails. A light is on or off. Classical physics reinforces this expectation. Systems possess properties whether or not you observe them. But quantum mechanics unsettles that assumption. At microscopic scales, particles are described not by definite states, but by wave functions, mathematical entities encoding multiple potential outcomes simultaneously. Before measurement, an electron does not occupy a single position in the familiar sense. It is described by a distribution of probabilities. Only when an interaction occurs, a detection event, a scattering, a registration on a screen, does a specific result appear. The formalism instructs you to calculate probabilities, then apply a rule. Upon measurement, the wave function collapses to one outcome. The equations work. The interpretation doesn't settle easily. Consider the iconic thought experiment proposed by Erwin Schrödinger. A cat sealed in a box becomes entangled with a quantum event. Until observation, the combined system is described as a superposition, alive and dead simultaneously. The scenario was designed not to endorse absurdity, but to expose tension. If quantum rules apply universally, why do you never perceive macroscopic superpositions? Where precisely does indeterminacy give way to definiteness? One response is the Copenhagen interpretation, historically associated with Niels Bohr. It treats measurement as fundamental. Classical apparatus, though composed of quantum parts, is assumed to produce definite outcomes. The act of measurement is not derived from deeper principles. It is taken as primitive. The theory predicts results, but refrains from describing underlying reality between observations. This pragmatic stance has guided generations of physicists, yet leaves philosophical discomfort intact. Another possibility eliminates collapse altogether. The many worlds interpretation proposed by Hugh Everett III suggests that all outcomes occur. When a measurement happens, the universe branches. In one branch, the electron is found here, in another, there. You experience only one outcome because you too become entangled with the result. The wave function never collapses. It evolved deterministically. Probability becomes a measure of branching structure rather than randomness. The cost is ontological extravagance, a vast proliferation of parallel realities. Other approaches modify the equations themselves. Objective collapse theories propose that wave functions spontaneously localize under certain conditions, especially at larger scales. Decoherence theory explains how interactions with the environment rapidly suppress interference between alternatives, making superpositions effectively unobservable. Yet decoherence alone does not select a single outcome. It transforms coherent possibilities into mixtures that resemble classical uncertainty without fully resolving the transition. You are left navigating layers of description. Mathematically, quantum mechanics provides amplitudes and operators. Experimentally, it yields definite clicks in detectors. Conceptually, it offers competing narratives about what is real. Does the wave function represent knowledge, physical reality, a tool for prediction? The theory's predictive success contrasts sharply with interpretive ambiguity. The measurement problem forces you to confront the boundary between physics and experience. A detector registers a value. A brain processes a signal. Conscious awareness reports a fact. At what stage does possibility become actuality? Is consciousness relevant, or merely another physical process obeying quantum law? Most physicists favor explanations that avoid special roles for observers, yet the puzzle persists because the formalism itself distinguishes between smooth evolution and abrupt collapse. You inhabit a world that appears definite, stable, continuous. Yet its foundational theory describes a realm of overlapping possibilities governed by linear equations. The bridge between these descriptions remains conceptually incomplete. Every time an experiment yields a specific result, you witness the unresolved transition firsthand. Quantum mechanics does not fail in calculation. It fails, perhaps, in narrative clarity. The measurement problem is not a gap in data, but in understanding. You can compute probabilities with astonishing precision. You cannot fully explain why one possibility becomes the reality you experience. The arrow of time. The laws of physics are largely time-symmetric, yet you remember the past and not the future. Entropy increases. Why did the universe begin in a low entropy state? The arrow of time may depend on initial conditions we cannot yet explain. You experience time as directional. Causes precede effects. Eggs break, but do not spontaneously reassemble. You recall yesterday, but not tomorrow. This asymmetry feels fundamental. Yet when you examine the core equations governing motion, from Newtonian mechanics to electromagnetism to quantum theory, most remain indifferent to temporal direction. Replace t with minus t, and the mathematics still holds. Where then does time's arrow emerge? Thermodynamics provides the first clue. The second law states that in a closed system, entropy, often described as disorder, or more precisely as the number of microscopic configurations compatible with a macroscopic state, tends to increase. A neat arrangement of molecules spreads into uniform distribution. Heat flows from hot to cold. Structures degrade without external input. This statistical tendency gives time a direction, from lower entropy to higher entropy. But the second law is not absolute in the same way as conservation of energy. It is probabilistic. Microscopic interactions remain reversible in principle. If you could track every particle precisely and reverse all velocities, entropy would decrease. The arrow of time arises not from the fundamental rules, but from boundary conditions, from how the system began. And this is where the puzzle deepens. Observations of the cosmic microwave, background radiation, mapped in detail by missions such as the Planck satellite, reveal that the early universe was astonishingly uniform. Uniformity in matter distribution corresponds to low gravitational entropy. Although hot and dense, the early cosmos possessed a special, highly ordered configuration. From that state, structure formation, stars, galaxies, the black holes drove entropy upward over billions of years. Why was the beginning so ordered? If the universe could have started in any number of configurations, overwhelmingly more, would have been high entropy states. A chaotic, gravitationally clumped cosmos would be statistically typical. Instead, reality began in a condition of extraordinary smoothness. The arrow of time you experience, memory, causation, irreversibility, traces back to that improbable beginning. Some physicists suggest that cosmic inflation, a rapid expansion phase proposed by Alan Guth, may help explain this uniformity. Inflation can stretch irregularities, producing large-scale smoothness. Yet inflation itself appears to require special initial conditions. The explanation shifts rather than vanishes. You move the question one step back. Why did inflation begin in the way it did? Others speculate that the arrow of time might be perspectival. Entropy increases toward what you call the future because you define the past as the direction of lower entropy. In this view, memory functions as a physical record encoded in present structures. Records correlate with lower entropy states. You remember the past because physical traces of it exist in ordered configurations, photographs, fossils, neural patterns. There are no comparable records of the future because those configurations have not yet formed. Still, this reframing does not eliminate the central mystery. It assumes a gradient to begin with. It does not explain its origin. On cosmic scales, the arrow of time shapes destiny. Stars exhaust their fuel, galaxies disperse, the black holes evaporate over unimaginable durations through processes described by Stephen Hawking. Entropy trends toward a maximum. The far future may approach thermodynamic equilibrium, a state of minimal structure and maximal uniformity, sometimes called heat death. Your psychological sense of time, your capacity for anticipation and regret, is entangled with this thermodynamic flow. Biological processes depend on energy gradients. Life exploits differences between hot and cold, high and low concentration. Without entropy increase, metabolism would stall. Thought itself presupposes irreversibility. The arrow of time is not written explicitly into most equations. It emerges from a fact about the universe's beginning, a fact not yet fully explained. You inhabit a cosmos whose deepest laws are symmetric, yet whose history is not. The direction you move through moments, the narrative of before and after, rests upon an ancient asymmetry embedded in initial conditions. Time flows forward because the universe started special. Why it did so remains one of the most profound unanswered questions in physics. Boltzmann brains. In an infinite or sufficiently large universe, random fluctuations could assemble self-aware observers out of chaos. Statistically, such observers might outnumber evolved ones. If so, it becomes possible that your memories are random fluctuations rather than records of history. Probability alone raises the question. You assume continuity. You assume that your memories correspond to real events, that your past unfolded in a coherent chain of causes, leading to this present moment. But statistical mechanics allows stranger possibilities. Given enough time and enough space, rare configurations become inevitable. Order can briefly emerge from disorder purely by chance. The idea traces back to Ludwig Boltzmann, who argued that low entropy states in a vast equilibrium universe could arise as fluctuations. If the cosmos were eternal and mostly in thermal equilibrium, then occasional pockets of order, even entire observable regions, might spontaneously appear. Our structured universe could be one such fluctuation, Yet the logic cuts deeper than Boltzmann intended. From a probabilistic standpoint, smaller fluctuations are vastly more likely than larger ones. It is far less improbable for a single self-aware brain to fluctuate into existence, complete with fabricated memories, than for an entire low-entropy universe to form. A fully formed, galaxy-spanning cosmos requires an immense reduction in entropy. A lone brain with illusory experiences requires far less. Such a hypothetical entity is called a Boltzmann brain. If the universe is spatially infinite, or if cosmic expansion driven by dark energy continues indefinitely, random thermal or quantum fluctuations could eventually assemble transient conscious systems. They would flicker into existence with detailed but false memories, impressions of childhood, history, scientific discovery, then dissolve back into chaos almost instantly. Statistically, if these conditions persist long enough, Boltzmann brains could vastly outnumber observers produced through billions of years of cosmic evolution. That creates a disturbing inference. If most observers in the universe are random fluctuations, then the typical observer would be one of them. And if you reason probabilistically about your own existence, you might conclude that you are more likely a fluctuation than the product of a long, lawful history. The argument does not claim that you are such a brain. It highlights a tension in cosmological models. Any theory predicting a universe dominated by Boltzmann brains seems self-undermining. If your memories are random noise, then your scientific reasoning about cosmology becomes unreliable. The very framework used to derive the conclusion collapses. Cosmologists therefore treat the Boltzmann brain problem as a constraint. A viable theory of the universe should not predict that typical observers are disembodied fluctuations. Models of eternal inflation, multiverses, or asymptotically expanding space-time must be constructed carefully to avoid this dominance. The measure problem, how to count observers in infinite settings, becomes central. You are forced to confront how deeply you rely on typicality assumptions. Science assumes that your observations are not wildly atypical. You trust that the regularities you infer reflect external reality rather than statistical accidents. The Boltzmann brain scenario exposes that this trust is not logically guaranteed. It is an assumption about probability distributions in the cosmos. There is also a philosophical sting. Your identity feels continuous because of memory, but memory is a physical configuration of matter. If configurations can arise spontaneously, then subjective experience need not track objective history. The link between consciousness and causality becomes contingent, not necessary. In practice, most physicists believe the universe's history, from low entropy beginnings to structure formation, provides a coherent account that avoids Boltzmann brain dominance. Yet the fact that serious cosmological models can drift into this paradox reveals how incomplete our understanding remains. You exist as an ordered pattern, embedded in a vast thermodynamic landscape. That pattern persists because of stable physical processes extending across cosmic time. The Boltzmann brain thought experiment asks what would follow if such stability were not required, if awareness could erupt briefly from equilibrium. Probability alone permits the possibility. Whether reality permits it in abundance is another matter. But the question lingers. Are your memories anchored in a deep past? Or are they statistical artifacts in a universe large enough to generate anything? Quantum fields. As fundamental particles feel like discrete objects, but in quantum field theory, particles are excitations of underlying fields that permeate all space. The electron is not a tiny marble. It is a vibration in a field. Matter may be patterns in continuous structures. You are inclined to picture reality as built from things. Tiny, solid constituents that stack and combine to form atoms, molecules, bodies, worlds. This intuition traces back to ancient atomism and survives in everyday language. We speak of particles colliding, orbiting, exchanging forces. Yet modern physics asks you to revise that image. In quantum field theory, the most successful framework for describing fundamental interactions, fields come first. A field is not an object localized at a point, but a value assigned to every point in spacetime. The electromagnetic field, for example, permeates the cosmos. Even in a vacuum, it is present. What you call a particle of light, a photon, is a quantized excitation of that field, a discrete packet of vibration. The same applies to matter. The electron is not a miniature sphere traveling through empty space. It is a stable excitation of the electron field, which exists everywhere. When you detect an electron at a particular location, you are observing a localized ripple in that field. Remove the ripple, and the field remains. The shift in ontology is subtle but profound. Space is not empty background, punctuated by objects. It is a dynamic arena filled with continuous entities whose excitations appear as particles. What feels like solidity arises from interacting patterns of vibration. The development of this perspective emerged through the work of many physicists, including Paul Dirac, whose equations unified quantum mechanics with special relativity and predicted the existence of antimatter. Later refinements produced the framework now known as the Standard Model, successfully describing electromagnetic, weak, and strong interactions in terms of quantized fields. One of the most striking confirmations of field primacy came with the discovery of the Higgs boson at CERN in 2012. The Higgs field permeates space, and its interaction with other fields endows certain excitations with mass. Mass, often imagined as intrinsic substance, there becomes a consequence of field interaction. Without the Higgs field's non-zero value, many particles would be massless, and the structures you depend upon would not form. Even the vacuum is not truly empty. Quantum fields fluctuate constantly due to uncertainty principles. Virtual, particle-antiparticle pairs briefly emerge and annihilate. These fluctuations have measurable effects, such as the Casimir force between closely spaced plates. Emptiness reveals itself as restless activity at the smallest scales. You might wonder how discreteness arises from continuity. The answer lies in quantization. Just as a vibrating string supports specific resonant modes, quantum fields support discrete energy levels. When energy is added or removed, it changes in packets. The field remains continuous, but its excitations are countable. This dual character, continuous substrate, discrete manifestations, challenges simple metaphors. If fields are fundamental, then identity becomes pattern-based. Two electrons are indistinguishable not because they share similar properties, but because they are excitations of the same underlying field. There is no deeper individuality beneath their behavior. What you perceive as multiplicity is repetition of a single structural possibility. This perspective reshapes your understanding of matter. Your body is not a collection of tiny beads, but a choreography of interacting fields. Electron fields binding to quark fields through photon exchange, stabilized by gluon fields within protons and neutrons. Stability is sustained resonance. Existence is organized vibration. The conceptual leap is difficult because perception evolved to track objects, not fields. Yet experiments consistently validate the field description with extraordinary precision. Collisions in accelerators reveal patterns predicted by field interactions. Anomalous magnetic moments align with theoretical calculations to remarkable accuracy. Particles feel tangible, fields feel abstract, but the abstraction may be closer to reality. What you call a particle is a localized event in something more pervasive. Matter is not made of things in space. It is made of excitations of structures that are space-filling. The world of solid objects dissolves into a deeper continuity. Beneath apparent discreteness lies a fabric of fields, and you, like every star and stone, are a temporary, stable pattern within that fabric. The limits of computation. Physical systems obey computational limits. Black holes suggest bounds on information storage. Landauer's principle ties information to energy. If reality processes information, it may be constrained by finite computational capacity. The universe may have a maximum resolution. You often imagine computation as something that happens inside machines, silicon circuits switching states, algorithms executing step by step. But physics suggests something deeper. Every physical process can be understood as information processing. The state of a system encodes bits. Interactions transform those bits according to lawful rules. If this is true, then computation is not merely a human invention. It is woven into the structure of reality. Yet computation is not unlimited. In the 1960s, Rolf Landauer demonstrated that erasing information has a thermodynamic cost. Deleting a single bit requires a minimum amount of energy proportional to temperature. Information is not abstract bookkeeping. It is physical. To forget is to dissipate heat. This principle ties logic to entropy, linking computation directly to the second law of thermodynamics. If information is physical, then storing it must also obey limits. Black hole. Physics sharpened this insight. When matter falls into a black hole, its information appears lost to the outside world. Yet quantum considerations suggest information cannot be destroyed. To reconcile gravity and quantum theory, physicists discovered that black holes possess entropy, proportional not to their volume, but to the area of their event horizons. This relationship, developed through the work of Jacob Bekenstein and Stephen Hawking, implies a maximum information density. There is a limit to how much information can be packed into a given region of space before it collapses into a black hole. Space is not an infinite storage medium. It has a capacity measured in bits per surface area. The implication is radical. Information scales with area, not volume. This insight led to the holographic principle, proposing that the total information contained within a region can be described by degrees of freedom residing on its boundary. Reality, in some sense, may be encoded on surfaces. You are accustomed to thinking of space as continuous, infinitely divisible. But if information storage is finite, then there may be a smallest meaningful scale, a limit to resolution. The Planck length sets a scale at which current theories lose predictive power. Below it, spacetime itself may not be meaningfully defined in classical terms. If you attempt to probe smaller distances with higher energy, gravitational collapse intervenes. Computation also requires time. Physical processes unfold at finite rates. The Margolis-Levitin theorem establishes a bound on how quickly a system with given energy can transition between distinguishable states. Energy constrains speed. Storage constrains capacity. Together, they imply that any finite region of the universe has a maximum computational throughput. You might ask whether the entire cosmos has performed a finite number of operations since its beginning. Some physicists have estimated this number using observable mass energy and cosmic age. The result is enormous but finite. If the universe is a computer, it is not an infinite one. These limits reshape speculative ideas. Perfect simulations of entire universes would require vast informational resources. Infinite precision measurements would demand infinite energy. Even thought itself, neural computation in biological tissue, consumes energy and generates heat. Intelligence operates within thermodynamic constraints. The suggestion that reality processes information need not imply a literal cosmic computer. It reflects the fact that physical states encode distinguishable configurations that evolve according to mathematical rules. But those evolutions are bounded. There are ceilings on complexity, speed, and density. You inhabit a universe that may not allow arbitrarily fine detail. At some scale, the questions lose operational meaning because no physical process can resolve them. Continuity may be an approximation emerging from discrete informational building blocks. Smooth spacetime could mask a finite underlying structure. The limits of computation do not diminish reality. They define it. Just as conservation laws shape dynamics, informational bounds shape possibility. Every star, every black hole, every thought unfolds within constraints set by energy, entropy, and geometry. The universe may feel boundless, yet its capacity to store, transform, and distinguish information appears finite. Reality might not only evolve, it might compute within strict and profound limits. The cosmic horizon. You assume the observable universe is the universe, yet light has only had finite time to reach you. Beyond the cosmic horizon, there may be regions forever inaccessible. What exists beyond cannot influence you. Your map of reality is permanently incomplete. You live in a bubble of perception. The light from stars, galaxies, and quasars travels across billions of years to reach your eyes or your instruments. The distance that light has traveled defines the observable universe. A sphere centered on your location, approximately 93 billion light-years in diameter. Beyond this sphere, photons have not yet arrived, and given cosmic expansion, many will never arrive. Those regions exist, perhaps, but they are causally disconnected from you. This horizon is not a philosophical abstraction, it is a physical boundary. General relativity and cosmological measurements reveal that space itself is expanding. Distant galaxies recede from you, and those beyond a certain velocity are moving away faster than light can traverse the intervening space. No signal, no information, no influence can reach you from them. They are, for all practical purposes, outside the universe you can interact with. You might imagine that what lies beyond is simply more of the same. Infinite repetition, perhaps, or exotic variations of structure. But you have no empirical access to confirm this. Any assumptions about the beyond are extrapolations, guided by the uniformity of the observable cosmos. You treat them as likely, yet they remain speculative. Reality beyond the horizon is unknowable in principle, not merely in practice. The cosmic horizon also reframes your understanding of time. Photons arriving from the edge of the observable universe carry information from when the cosmos was a fraction of its current age. Observing them is a form of looking backward, not in imagination, but in literal, measurable history. You reconstruct ancient events to infer conditions far away, yet you can never see what is now beyond the horizon. The present there, if it exists in a conventional sense, is permanently hidden. Inflationary cosmology complicates the picture further. According to inflation, the early universe expanded exponentially, stretching regions of space beyond each other's causal contact. The observable universe is a tiny patch within a vastly larger cosmos, a fraction of the total domain that may exist. Quantum fluctuations during inflation would have seeded density variations elsewhere, then producing structures and possibly entire pocket universes unreachable from your location. The horizon is not just a limit of perception, it is a fundamental constraint imposed by the universe's history. This horizon imposes profound epistemic limits. You can measure local properties, extrapolate large-scale structure, and even infer statistical distributions beyond sight, but you can never fully map out what lies beyond the boundary. Any hypotheses about distant regions must contend with permanent inaccessibility. You cannot send probes, you cannot receive signals. Your universe is defined as much by what you cannot know as by what you can. Cosmology confronts you with humbling questions. Are there other regions where the laws of physics differ subtly or radically? Are there vast structures, voids, or galaxies that will forever remain invisible to any observer? Even if the universe is infinite, your observational window is finite. Your experience of reality is a constrained perspective, a tiny lens through which an almost unimaginably large cosmos is filtered. The cosmic horizon also reframes existence itself. Isolation becomes inevitable over immense distances. The accelerating expansion, driven by dark energy, ensures that more and more galaxies slip beyond causal contact. In the far future, local groups of galaxies may become all that can ever be observed. Beyond that horizon lies an eternal unknown, untouched and untouchable. You are confined not by your technology, but by the fabric of space-time. The universe extends beyond comprehension, yet its distant regions cannot interact with you. Every measurement, every map, every theory is constrained to the sphere from which information has reached you. Reality is larger than experience. Your knowledge is necessarily bounded. The cosmic horizon reveals an unsettling truth. The universe you inhabit is only a fragment, a limited window into a far greater expanse. What exists beyond may be vast, intricate, and entirely inaccessible. Your understanding of reality will always be incomplete, defined by limits imposed by light, time, and the expansion of space itself. False vacuum decay. Quantum field theory allows the possibility that our universe resides in a metastable vacuum state. A lower energy state could exist. If a transition occurred, it would propagate at near light speed, altering the constants of nature. No warning would arrive before it did. You experience the universe as stable. Atoms hold together, the stars burn in predictable patterns, chemistry operates according to familiar laws. Yet quantum fields suggest that what feels permanent may be conditional, temporary, poised delicately on the edge of a more fundamental reality. The vacuum you inhabit may not be the deepest minimum of energy, but a local one, a false vacuum. In classical physics, stability is intuitive. A ball in a valley rests at the bottom. Quantum mechanics complicates this picture. Particles and fields are subject to fluctuations, probabilistic jumps, and tunneling. Even a system that appears settled can, with small probability, transition to a lower energy configuration. For the vacuum, this is not a theoretical curiosity. It is a concrete possibility embedded in the mathematics of field potentials. The implications are staggering. A bubble of true vacuum could nucleate spontaneously anywhere. Once formed, the bubble expands at nearly the speed of light. Inside, the laws of physics, the constants governing forces, particle masses, and interactions would differ from those outside. Matter as you know it could no longer exist. The structures of stars, planets, and even atomic nuclei might disintegrate or reconfigure in ways incompatible with life. No signal could precede the arrival of this bubble. Its expansion occurs at light speed, meaning that causality offers no warning. You could be living comfortably, unaware, when the transition reaches your location. Every measurement, every calculation, every experience would be instantly obsolete. The universe would continue, but its inhabitants, you included, would encounter conditions utterly alien to what they expect. Physicists have attempted to estimate the likelihood of such an event. Calculations depend sensitively on properties of the Higgs field and the top quark mass, among other parameters. Current measurements suggest that the universe may indeed reside in a metastable configuration, perched precariously above a deeper vacuum. Yet the predicted decay timescale is enormous, far exceeding the current age of the universe. Still, statistical probability does not rule out eventual catastrophe. The concept forces a confrontation with cosmic contingency. Everything you take for granted, the permanence of chemistry, the reliability of physical law, is conditional. Stability is provisional, then guaranteed only by the improbability of a quantum fluctuation large enough to trigger decay. The universe's apparent permanence masks the underlying fragility of its vacuum state. False vacuum decay also reframes causality and survival. You imagine yourself as an agent within a predictable cosmos, yet the ultimate fate of reality may not respond to any choice or observation. The parameters that govern particle interactions, chemical reactions, and stellar evolution are themselves contingent. No preparation, no measurement, no engineering could avert the event. Its propagation obeys the laws of physics with brutal impartiality. Even as you ponder the vast timescales involved, the idea is intellectually disturbing. Stability on human, planetary, or even galactic timescales does not imply safety in the fundamental sense. The universe's deep structure, defined by energy landscapes of fields, allows for sudden, irreversible, and all-encompassing transformations. What feels solid and eternal may be a temporary configuration, balanced on a knife's edge of probability. False vacuum decay exposes the universe as both delicate and indifferent. Its physical laws and constants which allow life and structure, may be the product of chance, temporary arrangements within a broader, potentially unstable landscape. You live in the comfort of apparent permanence, yet physics warns that the foundation beneath existence is probabilistic, contingent, and ultimately unknowable until, perhaps, it is too late. The unsettling conclusion emerges: the cosmos is not guaranteed to remain as it is. Even the laws themselves are provisional. What you perceive as immutable may vanish in an instant, replaced by a reality that is utterly foreign, with no forewarning and no recourse. The problem of identity in a material world. If you are composed of particles replaced over time, and if those particles are excitations of fields, what persists as you? Continuity of identity may not reside in matter, but in patterns. Yet patterns can be copied, altered, or split. What defines you as singular? You experience yourself as a continuous entity. You remember childhood, recognize your body in a mirror, and feel that there is a you connecting each moment. Yet science complicates this intuition. Your atoms are constantly replaced. Cells die and regenerate. The oxygen you breathe, the carbon in your bones, the electrons in your neurons, all are transient. Over years, that almost every constituent of your physical body is renewed. If matter is fleeting, what maintains identity? Quantum field theory deepens the puzzle. Electrons, quarks, photons, everything in your body is not a particle in the classical sense, but an excitation of underlying fields. These excitations are temporary, localized patterns in a vast continuous medium. They come into existence, interact, and vanish. The stuff you are made of is not permanent. Identity cannot reside in immutable matter. It must reside elsewhere. Patterns emerge as a candidate. The organization of atoms into molecules, molecules into cells, and cells into neural networks produces structure. Your memories, habits, and thought processes are encoded in these patterns. Continuity might exist in configuration rather than substance, but patterns are fragile. That they can be disrupted by injury, copied in digital form, or replicated in principle by an artificial substrate. If the same pattern exists elsewhere, does that mean another you exists? The philosophical stakes are unsettling. If continuity depends on pattern rather than matter, then identity becomes contingent and distributable. Consider thought experiments like teleportation. If a machine scans your entire structure, transmits the data, and reconstructs it elsewhere with new matter, is the recreated person still you? Material continuity is broken, but pattern continuity remains. Does the pattern define identity, or is there something more elusive, a singular perspective, a private subjectivity that cannot be transmitted or duplicated? You also face the problem of degradation and change. Neural patterns evolve with experience, and your memories shift, your personality adapts, your preferences fluctuate. The you of today is not the you of yesterday. Identity cannot be a static configuration. It must be dynamic, resilient to alteration. Yet this raises questions. At what point does change produce a different self? When does the evolving pattern cease to be the same identity? Moreover, quantum mechanics introduces indeterminacy. Events at the microscopic scale, from ion channel openings in neurons to molecular vibrations, are probabilistic. If the behavior of your neural substrate depends on quantum fluctuations, then each moment of your consciousness may be partly shaped by irreducible chance. The patterns sustaining identity are not perfectly deterministic. They are statistical, emergent, and contingent. Memory adds another layer of complexity. You rely on recollection to define continuity. But memory itself is a physical pattern in a noisy, mutable medium. Memories can be false, misaligned, or altered. If identity depends on memory, it becomes as fragile as the substrate that encodes it. Pattern, persistence, and perception intertwine, yet none guarantees singularity. The problem extends beyond the individual. If multiple copies of a pattern exist, or could exist, then the notion of a singular self fragments. Identity may be a local phenomenon, a perspective anchored in a specific spatiotemporal region, rather than a property of an abstract pattern alone. Consciousness may be what privileges one instantiation of a pattern over another. You inhabit a world where material continuity is ephemeral, fields underlie matter, and patterns are mutable. Your sense of self persists despite constant replacement, but physics offers no guarantee of uniqueness. Identity may not reside in particles, nor in abstract structure alone, but in the fleeting, probabilistic convergence of matter, pattern, and experience. The question remains: what defines you as singular, and is that singularity anything more than an emergent illusion of continuity in a transient universe? Causal loops enclose time-like curves. General relativity allows solutions in which spacetime curves back on itself, forming closed, time-like curves. In such geometries, cause and effect may loop. While speculative, the mathematics permits them. Causality may not be as linear as experience suggests. You experience time as a straight arrow. Causes precede effects. Decisions produce consequences. History unfolds irreversibly. The dislinearity feels self-evident. Yet Einstein's equations of general relativity describe a more flexible space-time, capable of extreme geometries where this intuitive ordering breaks down. The notion of a closed time-like curve, a path through space-time that loops back on itself, challenges the foundation of causality itself. Imagine a world in which you could travel along such a curve. You leave your home, traverse a trajectory through curved space-time, and eventually arrive at the same point in your past. Your departure and arrival coincide in coordinate time, yet you exist in both segments of the timeline. The effect, your arrival, is simultaneously a cause of the departure. Logic itself strains under this loop. Actions that produce themselves seem paradoxical, yet the equations accommodate them without contradiction, at least mathematically. Kurt Gödel, in 1949, discovered a solution to Einstein's field equations, describing a rotating universe that contains closed time-like curves. Later work, including the exploration of wormholes and exotic matter, suggested that other configurations might allow similar loops on smaller local scales. These scenarios remain speculative and likely unphysical under realistic energy conditions, but they demonstrate that linear causality is not an absolute requirement of space-time structure. Closed time-like curves introduce what are known as causal loops. Information or objects can exist without origin, circulating endlessly within the loop. A book delivered from the future to the past could be studied and copied, then sent forward again. Where did it originate? The loop carries knowledge, yet its existence is self-contained. These loops violate conventional notions of cause preceding effect. Events might be consistent internally, yet paradoxical externally. The universe permits sequences that defy ordinary temporal intuition. Quantum considerations complicate the picture further. If a particle travels along a closed, time-like curve, standard quantum evolution must reconcile probability amplitudes with boundary conditions that circle back in time. Theoretical work suggests consistency constraints. Histories must align to avoid contradictions, a principle sometimes called the Novikov self-consistency conjecture. Yet even with self-consistency, the idea that outcomes are constrained to prevent paradox illustrates how profoundly space-time geometry could influence what counts as cause and effect. These concepts are not merely curiosities. They force reflection on the assumptions underlying experience. You believe memory encodes past events, decisions influence futures, and actions have independent causes. Closed time-like curves reveal that such intuitions might be emergent, valid only in space-times with trivial topology. In a universe permitting loops, linear narrative is contingent, not fundamental. Moreover, these geometries raise unsettling questions about identity and agency. If you encounter a past version of yourself, are you the same agent acting independently, or are you a manifestation of the loop? Free will becomes entwined with global space-time consistency. Every choice you make along the curve is constrained by its future consequences. Yet those consequences have already happened from the perspective of the loop. The distinction between cause and effect dissolves. Practically, such loops may be impossible to realize. Exotic matter with negative energy densities or conditions far beyond those found in our universe may be required. Nonetheless, the mathematics is internally consistent. The laws of physics, at least in principle, do not forbid causality from being circular. You inhabit a world where cause and effect feel sequential, yet deeper structures allow for loops in time itself. Your linear intuition is a local approximation within a broader set of possibilities permitted by the geometry of space-time. Past and future, origin and consequence may not be as distinct as they seem. What feels inevitable could already be embedded in a cosmic loop. Causal loops challenge the very architecture of reason. They suggest that chronology is a property of perception and local conditions, not an absolute. The universe you experience as orderly may be just one of many logical structures, some in which beginnings and endings are entangled, and causes become effects that beget themselves. The uncertainty, principle, precision has limits. The more accurately you measure position, the less precisely you can know momentum. This is not a technological limitation, but structural. Nature itself imposes constraints on simultaneous knowledge. Reality resists complete description. You assume that if you measure carefully enough, you could, in principle, determine everything about a system. Classical physics reinforces this belief. A particle has a definite position and velocity at all times. Then perfect knowledge would allow complete prediction of future behavior. Yet quantum mechanics reveals that the universe refuses such precision. The uncertainty principle, formulated by Werner Heisenberg in 1927, establishes a fundamental limit to what can be simultaneously known about pairs of conjugate variables, such as position and momentum, or energy and time. The principle is not a statement about experimental inadequacy. No matter how perfect your instruments, measuring one property more accurately increases the indeterminacy of its conjugate. Pinpointing the location of an electron with extreme precision ensures that its momentum becomes highly uncertain. Conversely, knowing its momentum precisely blurs its position across space. The universe encodes this limit in the fabric of reality itself. Measurement is not merely an act of observation, it is an interaction that shapes what can be known. This constraint is deeply unsettling because it undermines the notion of a fully determinate universe. In classical thought, objects exist with well-defined properties regardless of observation. In quantum mechanics, properties are relational and probabilistic until interaction occurs. The particle does not have a sharply defined momentum or position independent of measurement. Nature itself resists a complete, simultaneous specification. Reality becomes less a fixed tableau and more a set of potentialities, crystallized only upon interaction. Heisenberg's principle has profound consequences for our understanding of space, time, and causality. In the microscopic world, particles fluctuate, fields vibrate, and energy blips into temporary existence. These fluctuations are not merely artifacts, they are guaranteed by the structural uncertainty encoded in quantum theory. Virtual particles pop in and out of existence, mediating forces and creating a restless, dynamic vacuum. The universe at its most fundamental level is probabilistic, a dance of possibility rather than deterministic motion. The uncertainty principle also imposes limits on control. Attempts to confine particles tightly, as in atomic traps or high-precision measurements, inevitably introduce momentum uncertainty. Attempts to observe very short timescales produce energy indeterminacy. Even the act of observation changes the system. Observation and interaction are inseparable, meaning that knowledge and reality are entangled. You cannot step outside the world to inspect it from a godlike vantage. Participation is unavoidable. At larger scales, the effects of uncertainty are often negligible, giving the illusion of determinism. Macroscopic objects behave predictably because the cumulative uncertainties of constituent particles average out. Yet the principle reveals that determinism is emergent, not fundamental. Classical predictability is a shadow cast by an underlying probabilistic substrate. The universe you experience as continuous and orderly is built atop a bed of indeterminacy. Philosophically, the uncertainty principle challenges notions of realism and completeness. The idea that the world has properties independent of measurement is weakened. You may ask whether reality possesses definite attributes at all before observation, or whether the act of measurement itself co-creates what is observed. Your understanding of the past, present, and future becomes constrained by structural limits. Reality contains unknowable elements, and these limits are unavoidable, intrinsic, and irreducible. You are compelled to confront the impossibility of total knowledge. Even in principle, no observer can catalog every particle, every interaction, every momentum. Nature is not merely opaque, it is fundamentally resistant to exact description. The uncertainty principle tells you that reality is probabilistic at its core, that knowledge is limited by the laws of the universe, and that the quest for perfect certainty is doomed to encounter structural boundaries. In this way, the universe preserves mystery not by accident, but by design. In the incompleteness of physical law, you expect science to converge toward a final theory. Yet Gödel's incompleteness theorems demonstrate limits within formal systems. If physics is mathematical, there may be truths about the universe that cannot be derived from any finite set of axioms. Even a theory of everything may not explain everything. Science presents itself as a process of successive approximation. Hypotheses tested, refined, and ultimately unified into comprehensive laws. You assume that, given enough time, intellect, and observation, physics could reveal a complete, self-consistent framework describing reality. Yet mathematics, the language of physical law, carries inherent limitations that cast doubt on this expectation. Kurt Gödel, in 1931, proved that any sufficiently powerful formal system contains statements that are true but unprovable within that system. No finite collection of axioms can capture all truth about the structures it describes. If physics is ultimately mathematical, if the universe is encoded in equations, symmetries, and rules, then Gödel's insight applies. A theory of everything might describe fundamental interactions, particles, and spacetime geometry, yet still leave certain truths inaccessible. Some aspects of reality might be unprovable, undecidable, or formally inexpressible. The ambition of total comprehension encounters structural barriers. Knowledge may asymptotically approach completeness, yet never fully attain it. Consider the implications for prediction. Even with perfect understanding of physical laws, some phenomena may remain beyond deduction. Systems of sufficient complexity could contain behaviors whose outcomes cannot be calculated from first principles. Chaos, emergent phenomena, and undecidable sequences illustrate how local rules do not guarantee global predictability. The universe may harbor truths that exist independently of observation, yet cannot be deduced by any finite reasoning process. This incompleteness also reframes certainty. You may imagine that science gradually replaces uncertainty with precision, resolving paradoxes and filling gaps. But if axiomatic incompleteness is unavoidable, certain questions may have no resolution. Observers could confront phenomena that are consistent with all known laws, but irreducible to those laws. Reality might be comprehensible only in fragments, forever resisting a fully unified account. The philosophical implications extend to consciousness and self-reflection. Your mind is a complex physical system governed by the same laws, yet you experience thought, perception, and awareness in ways that might elude complete formalization. Gödel's theorem suggests that any system attempting to fully describe itself may encounter intrinsic limits. Just as mathematics cannot be both complete and consistent, a physical theory may capture vast domains of reality while leaving some truths unexpressed. Even theoretical ambitions like string theory or loop quantum gravity confront this boundary. These frameworks offer intricate mathematical structures that unify interactions and predict phenomena beyond direct observation. Yet no matter how elegant, they may inevitably leave certain questions unanswered. The theory itself may contain true statements about its implications that cannot be proven from the axioms it embodies. Nature's laws, as encoded mathematically, might carry intrinsic mysteries. In practical terms, this means that physical law has a horizon. Observation, calculation, and reasoning operate within finite limits. Some aspects of the universe might be forever inaccessible to deductive closure. No matter how complete a framework appears, the underlying mathematics guarantees that surprises remain. certain outcomes, configurations, or relations may be fundamentally undecidable, known to exist only as truth outside the reach of formal derivation. You are confronted with a universe in which lawfulness coexists with inherent limits. Science reveals vast, the astonishing structure, yet the ultimate totality may always lie just beyond the horizon of formal understanding. Even if a theory of everything exists, the existence of incompleteness ensures that not everything can be explained, predicted, or proven. The cosmos, in its mathematical depth, preserves its own mystery. Reality may be lawful, but it is not fully knowable. The universe is an arena in which structure, symmetry, and principle coexist with boundaries that reason cannot surpass. The incompleteness of physical law guarantees that some truth will remain forever beyond the grasp of finite minds, no matter how ingenious, patient, or diligent. The final equation, if it exists, may not be final in its implications,